Okay, so great, they've done this. Now, what's the maximum tension the cable has to withstand? So to find the tension in the cable, what we're going to do is take our FBD over here and solve this to find what that cable tension is, given what we know about everything else. So at any given point there on this cable, we're going to align the axes so that the y-axis points in the direction of the cable, okay? Because we want to solve for the tension in the cable, so it makes sense to sort of get that. If we put that, if we put the y-axis acting in the direction of the cable, then we know that Ft will only appear in one equation, and that makes it sort of easier to get things the way we want them in the final form. So Ft, sorry, let me finish here. Sum of forces equals ma, and there's our Ft going that way. This is our component diagram. So now we've got mg something theta, and this component is going to be mg something theta, and I think, let's see, that's going to be theta. So this is going to be cosine, and this is going to be sine. Okay, so now we do sum of forces in the x direction equals blah, whatever, we don't care. Okay, sum of forces in the y direction equals, you got, okay, that always scares me when that happens. What? Nope. Okay, Ft. Okay, so we have the tension force acting in the positive y direction. We have mg cosine theta in the negative y direction, and that's going to equal may. Okay, so now let's think. When we're at some point here, they are going to be accelerating. They're going to be accelerating towards the center. They need a centripetal acceleration like this, okay, which is going to be the positive in the positive y direction. So here we can take, remember our fundamental equation is a equals a, and in this case the y acceleration is the centripetal acceleration. And the centripetal acceleration is in the positive y direction because we define y, positive y is the direction the cable leaves Luke and Leia. Okay, so ay equals ac, and I'm going to plop m's on both sides so that now we can plug this in directly. So we go sum of, no, we don't need this. We don't need to do this. We want this. Okay, so tension minus mg cosine theta equals m times centripetal acceleration. What we're going to use here is v squared over r. R is pretty obviously going to be the length of the cable. Okay, so now here's the whole point. We can plug in for v squared. And so if we are at some point, we're going to call 3, and 3 has some, well, I mean, here's the point. You don't even worry about labeling it 3, okay? We're just at some point, at some angle theta, okay, which can be positive or negative. It's actually not going to matter, okay? But if you want to define it positive here, let's do that. Or that's positive theta, and they swing over to negative theta because of, I don't know, whatever. Okay, the point is when you're at theta, at an angle theta from vertical, then your potential energy changes. Well, let's see. Oh boy, I am totally doing this. I mean, I'm doing this ugly. Let's see. What we need to do is define a reference for H1 and H2. In part 1, it didn't matter. We just needed the difference between the two. But now we need to actually find some absolute reference for height so that we can describe our potential energy as we change with theta. And by the way, if you're thinking, wait, isn't the tension just greatest at the bottom? Yes, in fact, it is. Okay. So if you want to just say that, that's great. I'm just going to define, though, this is my 0 height level, okay? So then, in fact, H1 or H2, H1 is -4, so H1 is -4 meters, H2 is -3 meters. And what we can do is say K plus U at our point theta, okay? So these are values at this whatever point we're looking at on their swing. And then we want to look at, we want to make that equal to the sum of K plus U somewhere else. In this case, the easiest one to do is at the end, right? So because K2 is 0 and we have mgh2 is our total, well, so let me just make this clear, K2 plus U2, okay, which then means 1/2 mv squared, which is our kinetic energy there, plus at whatever point, our current V. And then our potential energy is going to be is going to be negative mg, and then it's going to be how far we are below the 0 point. So this is going to be r cosine theta. I'm making this problem, I feel like I'm making this problem harder than it has to be. But anyway, and then at the end, at point 2, we have 0 kinetic energy, and we have negative mg. Well, let's see, I said h2 is 3 meters, so actually I should say 0 plus mg h2. Ugh. So, where this gets us then is that 1/2 m v squared at some point is equal to mg times h2, and then I'm subtracting this side off over to there, so h2 plus r cosine theta. And then we can say v squared equals g times, or actually, sorry, it's going to be not g, it's going to be 2g times h2 plus r cosine theta. Okay, and let me get rid of this. Okay, let's see. Yes. Okay, and so we take this thing here, and I'm actually going to go one step further, and because we're going to plug in v squared over r here, right? So I'm just going to divide through by r right now and make that work. So v squared over r equals 2g, and then we have to divide the r into both sides, both parts of this expression. So that's going to be h2 over r plus cosine theta. Okay, so now we take this, and I want to express this as, well, all the way over here. Ft, I want to express this as tension is equal to m times v squared over r, and then we take our mg cosine theta and bring it over, so plus g cosine theta. Okay, so, wow. Actually, I'm going to take this. Oh, I'm just being, this is ugly. Okay, fine. So v squared over r goes in here. So what I'm going to get now is tension force is equal to mass times, and then we're going to have 2g times not h squared, h2 over r plus cosine theta. Okay, and that's this v squared over r here is this, and then we get plus g cosine theta. Okay, so the tension force is equal to, almost done here, I promise. I'm going to go ahead and pull out my mg, or I'll pull out my g as well, and then we get mg times 2h2 over r. Okay, so it's this plus 3 cosine theta. Okay, so now what this tells us is that the tension is maximum wherever this is maximum. And what you can see is that you get the maximum value of tension when theta equals 0. And if you saw that earlier, well, good. You avoided a lot of pain. So hang on. I feel like I'm not doing this right now. Oh my god, am I? Wait a minute, have I screwed this up? Oh, because h2 is a negative number, right? So this is, okay, so anyway, this is maximized. In fact, let me just switch colors again. No, not that way. Switch colors this way, there we go. So this is max at theta equals 0, and then Ft equals mg times 2h2 over r minus 3. No, plus 3. Okay? And h2 was, so this is going to be mg times 2 times, and h2 was negative 3 meters. Okay? So we said, this is like I've taken a problem and made it like 10 times harder. Okay. This is 5 meters is r plus 3. So what you get is this becomes negative 6/5, so negative 1.2. And so this is going to equal 1.8 is all this in here times mg. Okay, so which is 1.8 times, and then it's 120 kilograms times 10 meters per second squared. Okay, so am I right? Yes, I'm right. So 2400 minus, so this is equal to, right, this is equal to what I got before. 2160 newtons is the maximum tension the cable has to withstand. Okay, if this seemed like a long and torturous and bad, like I was just scatterbrained and making a lot of mistakes, if this whole solution seemed like that, this is the second time I've recorded a solution for this today, and this one is a lot better than the other one. So, yeah, sorry. All right, anyway, but there you go. That's the answer.